Assalamu alaikum, dear students. I hope you've been practicing well lately. If you remember in the previous two lessons, we were talking about simple harmonic motion. After that, we talked about a pendulum, of course. And pendulum, we said it is a mass that is attached to a string, or it could be a rod, of course. This mass, of course, swings back and forth. And of course, we said there is a restoring force as well. And of course, we said that there could be a spring sometimes as well. Or if we have a mass spring system, of course, where a mass is attached to a spring, of course, if it is horizontal, this mass would move back and forth and back and forth. And of course, that was, let's say, one of the simple harmonic motion, let's say. And that was one of the things. And of course, we said the restoring force in that spring or mass spring system was the elastic force, of course. And we also said that the restoring force is directly proportional with the displacement. But of course, they are in opposite direction. Yeah. And of course, let's say if the displacement is, let's say, to the right, and of course, the restoring force will be to the left and vice versa, let's say. All right, and of course we said that at equilibrium, at the point where, for example, if the spring is not stretched or compressed, then in that case, of course, the displacement will be zero. That is, we're talking about horizontal spring, let's say. And in that case, if there is no displacement, of course, the restoring force will be zero because there is no force, let's say, by the spring, okay? That was for that. And then, of course, if you remember, we reached this part here, all right? And now we have simple harmonic motion. If you remember, we said, when do we call, by the way, not all sort of, or types of motion, let's say, can be called simple harmonic motion. When do we call the motion of a pendulum simple harmonic, let's say, or the motion of something simple harmonic? We said there are three conditions for that, yeah? One of them, we said that, remember, there must be, let's say, or the object must be swinging back and forth around, let's say, the equilibrium position. That is 1 second. It has to be, let's say, it has to be in a straight line if it is, for example, a pendulum. And let's say, and then the other one, we said that the restoring force must be directly proportional to the displacement in terms of magnitude. But of course, they are in opposite direction. All right, and of course, we also mentioned that when the motion of the pendulum is, or the displacement of the pendulum is smaller than 15 degrees, of course, then we can call it simple harmonic motion. All right, otherwise it cannot be called simple harmonic motion. All right, so today we have this, yeah? And of course, for the spring, we did explain this one, yeah? But if we have a pendulum like this, when do we call simple harmonic motion? Or what are, like, what will happen to the restoring force, what will happen to the acceleration, to the velocity, kinetic energy, momentum, potential energy, and all that, okay? So let's discuss this and consider each one of these and see what happens in each one of them. Let's say we have a pendulum here. Let's say this is, of course, this point here, you can call it the restoring or the point where the pendulum is at rest, no movement here. But when the pendulum is set in motion here, let's say here's the pendulum, yeah? And of course, we can consider 3 points in here. Let's say that is one of the points. You can call this one point A at maximum displacement here. Point B here would be at, let's say, minimum displacement, or when the displacement here is zero. And of course, we can take point C, right, which is the same as the other point, of course. Or you can say, when the pendulum is at both extremities here, you can call these maximum displacement. And by the way, in pendulum, of course, the displacement is measured by what? By this angle here, okay? So, of course, the maximum displacement would be when this pendulum is displaced with the maximum angle here. Okay, and of course, we'll talk about the restoring force and all that, like, in more detail. That is one. And then, of course, if we have, let's say, 2, and then let's say this one as well. We have another situation where the pendulum, let's say, here's the pendulum. Now, this point here, let's say, it was right here, but now it is at a point here which is moving towards the equilibrium here. So this is point A. At this point right here, it is moving towards the equilibrium, don't forget. And of course, after that, it might pass, or it will pass into the other, let's say, the other side before it swings back and forth, as you can see here. And then let's say at another point here where the pendulum is right at this point here, where the displacement is zero, don't forget. Okay, so the pendulum was here when we let it go, when we let it start swinging. So now, let's say from this point, it went all the way to this point here. And then after that, of course, we can say what happens when it leaves the zero displacement or minimum displacement. And of course, it is swinging, let's say, past the equilibrium. And of course, it is going towards the maximum displacement at the other side here. Okay, so bear with me here. Remember, first of all, before we talk about this, do you remember the restoring force in pendulum? What was the restoring force? We've mentioned before that in elastic or in springs, of course, the restoring force, let's say if that was the spring here, and this is the original, or the point where the displacement is zero here, and of course if the spring is extended, and here's the mass, okay, we said you have to stretch the spring this way, correct? That is basically the displacement, okay? And of course there was a force that was trying to bring the spring back to its equilibrium position. What was the name of this force? Of course it was the elastic force, which is provided by the spring. And of course this force, or you can say the stiffer the spring, or the bigger the value for the K, the more the force you need to extend the spring or stretch the spring. And of course this force that is trying to restore or trying to bring the spring back to original or zero displacement would be bigger as well. So this force that tries to bring the mass back to its equilibrium or zero displacement, we call it the restoring force. And of course it is provided by the elastic let's say this force, or the name of this force is the elastic force, which is provided by the spring here. So, but that is not the point that we're discussing here. Okay, so let's go back to the pendulum here. Remember that the restoring force in here, okay, the restoring force here is, by the way, let me redraw this one for you here. Remember, this can be analyzed to, all right, this can be analyzed to components, yeah? This mass, of course, or this bob, oops, not again. Okay, so this bob has a mass, of course, and of course mass times gravity gives us a force, yeah? That is the weight of the object, which is, you can say, the gravitational force. But of course, this force will be analyzed to two components, yeah? One of them like this, and of course the other one can be analyzed like this one here. So you can see that there is tension here in the string, of course, and then this one is here, of course, this one is going to be mg, but because the angle is with this here, we know that the angle that is attached, or the angle that, for example, attached to the side that we're taking, of course, would take cosine here, so mg cosine theta. Okay, this mg cosine theta would be equal to the tension here, so this two will cancel out. So what is left in here is this component of the weight of the object, which is in this case mg sine theta, is what brings the object back to equilibrium position here, or let's say where the towards the let's say zero or minimum displacement. So of course we call this component of the force, we call it the restoring force. And by the way, in the spring, this component, or this, was the elastic force, yeah? But here, of course, we have the component of, you can say, the weight of the object in here. So you can call this one gravitational force. Instead of mg, we can say fg. That is because this mg equals to the force or gravitational force, the weight of the object, and then times sine theta, of course, okay? So we can say that what can we say about the restoring force? Of course, we can have a question here. What does the restoring force depend on, yeah? Of course, if it is on Earth, we can say the restoring force depends on the mass of the bob, and of course, it depends on the angle or the displacement angle here as well, okay? Of course, we can just say the angle here to be on a safe side. Now, let's go back to this. Now, how do these forces, acceleration, the energy, by the way, when the bob is at the highest point, what type of energy do we have? So let's clean this a little bit in here. Take a look. When the bob is at the highest point here, remember, do we have elastic potential energy here? No. The type of the energy that is here, it is called gravitational potential energy here, okay? So of course we have a few things here. Remember this, yeah? We have, let's say, let's consider each one of these, yeah? Of course, at this point here, we have the restoring force, which is Fg, of course, And we can say the acceleration here, and of course we have the gravitational potential energy here, we have the angle theta, that'll be the displacement of course, and then we have the velocity or the speed in here, and then we have kinetic energy, and of course we could have momentum as well. Remember, each one of these, or all of these, are maximum. Because remember, the highest point or the furthest point from the equilibrium, that is maximum displacement. At maximum displacement, Fg is going to be maximum. Why? Because Fg, you do know that Fg, or this restoring force, equal to what? Equal to mg sine theta, yeah? And of course, the bigger the angle here, that means the bigger the restoring force as well. Okay, what about the acceleration? The acceleration and force are directly proportional. So bigger force, that means bigger acceleration, and you do know that. What about the gravitational potential energy? Remember, the potential energy, the energy that is stored inside this system, of course, at this point, before we let it go, it is solely potential or gravitational potential energy. So it's not the same as the one that we had here. The potential energy that we had for a spring was elastic potential energy. Why? Because this spring was stretched and it is elastic. But here, rather being stretched, of course, we have the height of the pendulum will change. And you do know that when the height changes, then we will have gravitational potential energy, or you can just say potential energy for short. Okay, and then that is acceleration is maximum, gravitational potential energy is maximum. At the highest point, this angle theta, of course, it is maximum as well. What about the velocity here? At the moment before we let it go, there is no velocity, there's no motion, there's no speed. So of course we can say these are zero. If velocity is zero or speed is zero, then of course we can say kinetic energy is also zero, because kinetic energy is 1 over 2 mv squared. And then what about momentum? That is mass times velocity, which is no velocity. That means the momentum is also zero. So we can say at a point here, or the highest point, okay, at the highest point here, these values are zero, these values are maximum, and then these values are minimum, or you can just say zero. Okay, now what happens as the pendulum starts to swing or tries to get closer to the equilibrium position here? All right, now I want you to take a look here. So remember, those values that we were saying that these were maximum, of course, do you think they will stay maximum after the pendulum has started swinging, let's say? Of course not. So we can say the restoring force, let's say Fg here, and of course we had acceleration, and then we had gravitational potential energy, of course, and then we had angle theta, and then we had velocity, of course, we had kinetic energy, and then we had let's say momentum as well, which is mass times velocity. Remember, these values are going to decrease here, okay? Why? Because now they are not at the highest position anymore. We're moving towards the equilibrium. So these values are going to decrease, remember, okay? Decrease, or you could just do an arrow down, that is, these values are going to decrease. What about these values? Of course, now it has started to move here, of course, it is gaining momentum. So the more, or the closer it gets to the equilibrium position, of course, you can say, or at zero displacement, the faster the speed becomes, you can say, yeah? You can call it velocity if you consider the direction here as well. Okay, so we can say that these values, or each one of these, are going to increase, okay? Increase, or an arrow up, that means increases, okay? Now, what about, so the restoring force will be less, the acceleration will be less, gravitational potential energy will be less, angle theta will be less, and of course, speed, kinetic energy, and let's say momentum, these are going to increase in terms of magnitude. Okay, now, what about when the object is right at the equilibrium, or when the displacement is zero, of course? So what happens when the displacement is zero? Now, I want you to think of, you know, like a point where there is no motion. Remember, if there's no motion in here, if this is the pendulum, remember, if there's no motion here, of course, there is a gravitation, there is a weight, or gravitational force, which is downward, yeah? Fg, that is going to be mg, which is downward, yeah? But then what is the force upward? The force upward, of course, is going to be F tension, yeah? Or just tension, you can call it. But we said that Fg, or the restoring force, equal to mg what? Mg sine theta, correct? But what is the theta here? There is no theta, or you can say the angle is zero here. So at this point here, there is no restoring force at the equilibrium, remember, okay? That is even true when the pendulum is in motion as well. Okay, but this pendulum keeps swinging past the 0 or this equilibrium position, and I'll tell you why is this in a second. All right, moving on to this part. So what do you think will happen to the velocity, to the restoring force and all that, yeah? And of course, remember, we're talking about restoring force, we're talking about acceleration, GP and all that. So at this point here, we can say, if I write it here, the restoring force, the acceleration, the gravitational potential energy, gravitational what? Gravitational potential energy, and of course we can say angle theta, and then again velocity, kinetic energy, and momentum as well. Remember, each one of these values are going to be what? Going to be minimum, or you can just say these values are going to be 0. Why 0? Remember, the restoring force is going to be 0 because there is no angle here. Restoring force here is equal to mg sine theta. What is the angle here? 0. Sine of 0, of course, is going to be 0. So Fg, the restoring force, is 0. What about the acceleration? If the force is 0, what do you think about the acceleration? Of course, that must be 0 as well. What about the GPE, gravitational potential energy? Previously, it was at this point, let's say height, yeah? At a point here is going to be minimum height based or considered to this point, of course, we say gravitational. We can consider that this level here, we can consider this level to be 0 GPE, yeah? So at this point, we assume that there's no height. And if there's no height, of course, there's no GPE. What about the angle theta? You can see here there is no angle here, or the angle is 0, so minimum or 0. What about the velocity here, or speed in this case? We can say, by the way, you might hearing me change or use, like the two terms here. Let me just go with the speed, so we don't care about the direction here. Okay, remember at a point here, all the energy was only gravitational potential energy. But at a point here, if we assume that there is no air resistance or friction, all this GPE, all right, GPE will be converted into what? Into kinetic energy. And in that case, of course, at this point here, the velocity here is going to be what? Is going to be maximum here. If the velocity is maximum, of course, the kinetic energy will be maximum. And of course, the momentum here is going to be maximum as well. So remember this. At a point or the highest point, remember these values, all right, that is the restoring force, acceleration, gravitational potential energy, and theta. These are maximum, and the other values will be minimum or 0. At the point here where the object is passing, or right at the equilibrium point, or where the displacement is 0, all these will change, or you can just swap them here, which means that Fg, acceleration, gravitational potential energy, theta, all of these will be 0, and then other values will be, or variables, of course, will be maximum here. What about when it passes, let's say, through the equilibrium? What do you think will happen? Now, of course, now these values are going to increase. So Fg, when it passes through this is the equilibrium, yes? When it passes through the equilibrium, of course, at a point here, okay, Fg are going to, like for example, going to increase because it is in motion. It's going to get higher and higher and higher. So of course, each one of these values are going to get bigger and bigger. So Fg, right, and acceleration, GPE, you can say, GPE, and then of course angle theta, these are going to be what? Going to increase, okay? Going to increase, and then other values like speed, kinetic energy, and of course momentum, these are going to what? Going to decrease again until they keep decreasing until it reaches the highest point, and at the highest point, of course, is going to be 0 for these values, and these values will get maximum, just like what happened at the other side. So we can say at these two sides, let's redraw all this, okay? So let's say here's the pendulum, okay? Let's change the color here. What do we have? We have a pendulum here, okay. Didn't change. Okay, so here is a pendulum. Remember this. This is the highest point, you can say. And of course, let's say this equilibrium or the displacement is 0, and then this is the highest at the other point as well. You can say at both extremities or at both ends, here and here, the restoring force, acceleration, gravitational potential energy, and angle theta, these will be maximum here. And at a point here, and you can say the energy here, it is solely gravitational or GPE here, okay? And at a point here, right at the middle here, where the displacement is 0, remember, the speed, kinetic energy, and momentum will be maximum, restoring force, acceleration, let me just rewrite it. Fg, all right, acceleration, and then gravitational potential energy, and then angle theta. These are what? These are maximum, okay? And these are true for both sides, by the way. And of course, we have, let's say, speed, kinetic energy, and momentum. These are going to be minimum, or you can just say 0. But at a point here, remember, Fg and acceleration, GPE, and angle theta, these are going to be what? Going to be 0. And what will be maximum is speed, kinetic energy, and of course momentum as well. These are going to be maximum here. You might wonder, what about a point in between this, yeah? Let's say we have a point here. What do you think will happen, by the way? If it is a point here, by the way, we said it that at these two extremities, all the energy that we have, it is just gravitational potential energy, but the energy here, it is solely kinetic energy. Okay, now, what about a point here? Of course, at a point right in the middle, we will have both gravitational potential energy and then kinetic energy as well. But remember, it's very important to consider the type of the or the direction here, because if it is moving this way, of course, gravitational potential energy is converting into kinetic energy. Gravitational potential energy is converting into kinetic energy. But if you take a point here, and if the motion is in this direction, kinetic energy is converting into gravitational potential energy. That is a slight difference between the two here. And in regards of the other values here, these will decrease as it go from this point to this way, but at a point going to the other side, they are going to increase here. Okay, so just remember this. There will be questions that might tell you, for example, what will happen to the restoring force and the acceleration for when the bob of the pendulum, for example, it is heading towards the equilibrium, let's say. And in this case, of course, the Fg, it is going to decrease, the acceleration also going to decrease. But if it is the other way around, of course, then it has to increase in this case. All right, so I hope that was clear as well. And then you might wonder if the restoring force at this point is 0, okay? If that is the case, then why the object is moving past the equilibrium? And of course, I do believe that, the reason why is because the object already set in motion. The object is moving already, and you do know that when we have mass and velocity, of course, we have momentum. So you can say because of the momentum, the object moves past, let's say, this point here. Or you do know that when an object is moving, you can say it has, another way to say this is because it has kinetic energy, which it keeps it moving, let's say, at a point or at this point here. So this is exactly what we've explained there. Take a look at we have the quantities, and of course at maximum displacement, that is going to be a point here. And towards the equilibrium, that is going to be somewhere between maximum and equilibrium here. And of course, this is at equilibrium position where x is 0. And then this is when, let's say, moves away from the equilibrium there. Now, one thing that is very important, I want you to know this, is this. Let's say this is energy conservation in a pendulum. Remember this. If we assume that the system is ideal, or if we disregard the air friction and the resistance, of course, once the pendulum is set in motion, it will, let's say, keep swinging forever. When does this happen? When the system is ideal, when there is no air resistance, when there is no friction, let's say. But you do know that in real world or physical world, let's say, this doesn't happen because, of course, there's air resistance and friction of, let's say, between the string and, of course, the point where it is suspended. So it keeps slowing down more and more until the pendulum eventually stops here. So, but one thing, if we assume that the system is ideal, for example, then, of course, one thing, of course, that was one of the exotic questions as well, the total energy of the system doesn't change or always remains the same. Okay? What is the total energy of a pendulum? Remember this. When we have a pendulum, of course, let's say the total energy, that is going to be mechanical energy, which is equal to potential energy plus kinetic energy, correct? At a point here, all the energy is, you can say at a point here, all the energy, let's say, let's change this one here. At a point here, all the energy that we have, it is potential energy. So mechanical energy here equal to potential plus kinetic, where kinetic is 0. At a point here, okay, you can see that we can say mechanical energy equal to potential plus kinetic, but potential is 0, so all the energy is kinetic here. What about a point here? Again, mechanical energy equal to potential plus kinetic. So potential is maximum, kinetic is 0 here. So one thing that remains the same is the mechanical energy, which means that the kinetic or the potential energy and kinetic are always changing. What about a point here, let's say, somewhere in between? And of course, if that is the case, we can say, let's say the mechanical energy is 10 joules. That's very little, but still, yeah? If it is 10 joule, at a point here, it is only, this 10 joule will all be gravitational potential energy. At a point here, it's going to be 10 joules of kinetic energy. At a point here, it's going to be 10 joules of potential energy again. But what about a point that is in between the two? Of course, it's going to be 5 and 5. So we will have both potential energy and kinetic energy as well. Okay, so remember this. So what we have, if you look at this diagram, that is what we have, let's say. And of course, that is the pendulum here, right? So this is the energy, of course. Yeah, this is, let's say, for part A. You can see there. Okay, I'll show you what it means. Yeah, this part B and this part C as well. And of course, it would be best if we draw a pendulum here, let's say. That is right at the equilibrium here. And of course, we have a point here. And of course, we can go to a point there as well. Look, when this pendulum is swinging, let's say, at a point here, we have maximum potential energy here. As you can see here, this line here, it represents the potential energy because at a highest point, it is not in motion yet. So all this energy is potential energy. As it starts to swing here, now at a point here, all this energy will be converted to kinetic energy. And then as it goes all the way to the other side, this kinetic energy will be converted again into potential energy as well. But at a point here, right in between, of course, we can say all the total energy that we have is half potential and half kinetic as well. Like we said earlier, if it is 10, it is going to be 5 kinetic, 5 potential, and that is what we have. But if you look at this line right here, okay, you can see that this one here, this value, which is the total mechanical energy, you can see that it is always constant. What does it mean? That means the total energy of the system is constant, but potential energy and kinetic energy are always changing as long as the object is, or the pendulum is in motion here. Okay, now let's solve a few questions here. Take a look, these are very important. It says, when vibrating, the simple pendulum's bob reaches the equilibrium position. Yes, remember. Which of the following values are maximum? Remember, it is vibrating, so it is not in, let's say, not stationary. The simple pendulum bob reaches what? Reaches the equilibrium position. So if this is the pendulum here, okay, it was at this point here. Now it is moving towards this position here. So at this position here, which one of these values, the following values are maximum? Is it the gravitational potential energy? No, because gravitational potential energy, or the height here is maximum. So of course, maximum gravitational potential energy would be maximum at this point. Is it at the highest point? No, it is at the equilibrium. So this bob is at this location here. So can we say gravitational potential energy is maximum? No. What about C? Can we say the restoring force is maximum? No. Remember, restoring force is maximum at this point here. At the equilibrium, the restoring force is 0. What about kinetic energy? Yeah? Can we say the kinetic energy is maximum? Of course. Why? Because velocity or speed at this point is maximum. If speed is maximum, of course, that means kinetic energy will also be maximum as well. So, of course, B is correct. What about D here? It says tangential acceleration. That is, of course, not as well, okay? Because remember, we said at this point, acceleration is 0. If the acceleration is 0, that means that the tangential acceleration will also be 0 as well. Okay, now, look at the second question. It says, the restoring force of a vibrating pendulum is what? Remember, do you remember what was the restoring force? We said it was the, let's say, the tangent to the component, or tangent, or was one component, let's say, of the gravitational force, and of course, let's say, it was, what was it? It was Fg sine theta, yeah? Or you can say mg sine theta, that is also correct. But what we have here is Fg sine theta. Remember, this Fg, that is mg, correct? Mg sine theta would be the component. That is what we call it, the restoring force in pendulum. Okay, can we say cosine? No, that was the component that cancels the effect of the tangent. Tan, no. Elastic force, no. Elastic force would be, remember, elastic force would be the restoring force for the spring or mass spring system here. Okay, take a look at this question here. It says what? In which of the following the motion of a simple pendulum is simple harmonic motion? Remember, if it is a pendulum, in order to call a simple harmonic motion, the angle or the displacement cannot be bigger than, or the angle cannot be bigger than 15, cannot be bigger or even equal to 15, by the way. It has to be smaller than 15. So you can see here 45 is too big, of course. Yeah, 90 is too big, 60 is too big. What about A? Of course, we can say A is the correct one. Take a look at the fourth question here. It says, which of these periodic motions are simple harmonic motion? Okay, remember, we can say every simple harmonic motion can be called periodic, but not every periodic can be simple harmonic motion here. So it says a child swinging on a playground swing angle, or where the angle equal to what? 45 degrees. That is bigger than what? Bigger than, let's say 14, yeah? Okay, which is, cannot be considered that. A CD rotating in a player about a vertical axis. And of course, not because you can see that it is just rotating. So there's no simple harmonic motion here. What about C? An oscillating clock pendulum at an angle of 30. That is also too big. What about an oscillating clock pendulum? Let's say the angle equal to 10 degrees. And of course, we can say that this is the correct answer here. Okay, moving forward. It says, which of these periodic motions are simple harmonic motion? That is section review, of course, question 1. Which of these periodic motions are simple harmonic motion? A child swinging on a playground, we said this angle is too big. A CD rotating in a player, that is not. Okay, an oscillating clock pendulum angle, where the angle or theta equals to 10 degrees, we can consider this. Okay, now, take a look at the second question. It says, how does the restoring force acting in a pendulum bob changes as the bob swings towards the equilibrium position? Remember, this is not at the highest or maximum displacement. There's a point where it is moving towards the equilibrium. So if I redraw this, or draw the pendulum for you, let's say, if this is the pendulum, let's say, this is the highest point, yeah? And this is the equilibrium position. At a point here, this pendulum bob is moving towards the equilibrium, yeah? So how does the restoring force at this point is changing? Remember, at a point here, we can say at this point, the restoring force, Fg, is going to be maximum, yeah? So what about a point here? At a point here, of course, let's say this point, Fg is going to what? Is going to decrease. What about at equilibrium? At equilibrium is going to be 0, yeah? So of course we can say the restoring force is going to decrease as it moves or as it approaches the equilibrium position. So the restoring force decreases. If the restoring force decreases, of course, the acceleration will decrease with it as well. Okay? But the velocity, we can say, increases, yeah? The question is just about the restoring force, by the way. We have another question, says, critical thinking. When an acrobat reaches the equilibrium position, the net force acting along the direction of the motion is 0. So how come, or why does the acrobat swing past the equilibrium position here? Remember this, because we said the acrobat, it is in motion, yeah? And of course, when it reaches the equilibrium position, it is true that the restoring force is 0, yeah? But why does he continue or keeps passing through the equilibrium? That is because it is already set in motion, it has a velocity, or you can say it has kinetic energy, or you could just say because it has momentum, which is mass times velocity. Newton's first law of motion, of course, it is going to continue move, and it is, let's say, then in its path, yeah? Or because of it is momentum, it keeps moving. So the momentum of the acrobat carries them past through the equilibrium position. Okay, and of course you do know that momentum equal to mass times velocity there. Okay, now, a new section here, how do we measure simple harmonic motion? Okay? Now, of course, one of the things that we have is called amplitude, yeah? How do we define amplitude? If you remember amplitude, perhaps in grade 10, let's say, or grade 9, actually. Okay, so we can define amplitude as the maximum displacement from the rest position. That is one way to define amplitude, yeah? So if it is, so remember this term, amplitude is the maximum displacement from the rest position, okay? Now, let me give you another, now, try to think of this example with me. If we have a spring or mass spring system, When do we have maximum amplitude? Yeah? Of course, maximum displacement, not maximum amplitude. So amplitude is maximum displacement. If you have a spring, for example, once you stretch it the most, okay, that maximum displacement, or when the spring is stretched the most, okay, then of course we can call this maximum amplitude. Why? Because it has moved away from the equilibrium position. Let's say if this was the, let's say, let's use this, okay? Now let's give, okay, now take a look at this. Let's say we have a mass, okay? And of course, if this is the equilibrium position, what happens when you stretch the spring? Of course, you're going to, let's say, the spring has stretched this much, or let's say extended this much, yeah? So if this is a point where the displacement is 0 without any mass, but now it is being stretched here, so this here extra, or like this much that is stretched here, so you can call this one maximum amplitude here. So this is going to be the amplitude of this mass spring system. Why? Because it is stretched, or this stretch where x is maximum away from the equilibrium. By the way, what happens if you, for example, compress the spring? Of course, that is also true. Let's say if this is the equilibrium position, and of course, if you're going to compress it this much, let's say this maximum displacement in the other direction can also be called the amplitude. Now, what about for the pendulum, by the way? Yeah, let's say here is a pendulum. If this is the equilibrium position here, and of course, if you're going to, for example, move the pendulum to a point here, this by the way, this, you can see that the bob is at maximum, or maximum displacement from the rest position here, or equilibrium position here. So this angle here, by the way, the amplitude measured in, you can say, in displacement here, okay, but the amplitude here is measured with the angle here. So the bigger, or the biggest angle that we have here, of course, you can call this one maximum amplitude here. And remember, later on we're going to study if we have a wave, let's say, and this is basically the rest position of a wave, yeah? So if I have a wave like this, this is the rest position of the wave. So the maximum amplitude, whether up or down, of course, this is also can be called amplitude. By the way, this is a displacement as well, yeah? But can we call a point here maximum or amplitude? No, because amplitude is the maximum displacement from the rest position. So this point here can be called maximum, can be called amplitude. At a point here can also be called amplitude, but not this point or not any other points closer to the rest position there. So, and of course we have, let's say, okay, I hope these are clear enough now. So what is amplitude? It is the maximum displacement from the rest position, from the equilibrium position, that can also be considered. Okay, so the maximum displacement from the equilibrium. Remember this, if it is the pendulum's amplitude, of course, it can be measured by the angle between the pendulum's equilibrium position and, of course, and the maximum displacement. But if it is for a mass spring system, we said the amplitude is the maximum amount of the spring that is stretched or compressed from its equilibrium position. Now, we have two other terms which are also important. And these two terms are period, and frequency. So what is period? Now, in a simple definition, we can say period is the time it takes for one complete swing, yeah? Let's say we have a pendulum, yeah? Give me a second. Let me bring this one to present or to help you better. Let's say that I have a mass, and of course there's a string that is attached, yeah? Let's say here is the pendulum. If I let it go, it swings, let's say, this and then go back, yeah? Imagine this. It goes all the way, that is half a cycle, and then it comes back all, let's say, to the point where my hand was. And that is, of course, called one period. Remember, let me draw this one for you again. So we have what? We have period, yeah? So what is period? In physics, of course, period is the time for, okay, so let's say here is a rest position. Of course, the pendulum can be here, and of course, it can go all the way to the other end. So the time it takes for the pendulum to, from this point, to go all the way, now that is one point here, and then all the way back to the other side, for example, that is called what? That is called one, or just period, let's say. That is called what? Called period, which is the time which is the time for what? The time for one complete swing, okay? Now, let's analyze this again. Remember, in order to do this, it has to go all the way. Let's say I'll let it go at this side here. So go all the way to the other side and then back to the side. That is basically one swing. And the time it takes to do or to go all the way to the other end and come back, that is basically what we call a period. So let's see. See, that is one period. One period, two period, yeah? So going all the way to the other end and back to my hand, that is basically the time for one complete cycle or just one period. You can see 1, 2, 3, 4, and all that, yeah? Of course, the time for one swing is what is called period, yeah? Now we have, so we can say, that is for that, yeah? So period, of course, we use T for that, and of course, that is measured in second as well. But take a look. Do you know that period and frequency are related? So what about frequency? How do we define frequency? Frequency is the number of vibrations per second. What is frequency? The number of vibrations per second. For example, let's say, you could have a string, let's say, yeah? How many times does it vibrate in 1 second? That is called frequency. In terms of, if we're talking about pendulum, of course, how many times does it go back and forth, let's say, in 1 second? That is called frequency. Again, take a look. Let's say, in 1 second, if we say, how many times does it go back and forth, back and forth, back and forth? That is basically called frequency. So frequency is the number of vibrations or the number of waves per unit time or per second. So we can say frequency equal to 1 over the period. Frequency is measured in what? Measured in hertz. Okay? But remember this, okay? We can say if frequency is measured in hertz, so we can say hertz is equal to 1 over second, correct? Can I say hertz is equal to, if we take this second up, what will happen? It becomes second negative 1, yeah? So can I say hertz equal to negative or second power negative 1 as well? Yes, that is also true. What if it is the period? Period equal to, by the way, these two we can swap or change their location. If you use cross multiplication, we can say period equal to 1 over f, correct? Very, very good. So, but what is the unit for time, for period? That is second, yeah? Can we say second equal to 1 over hertz? Yes. Can I also, what happens if I take this hertz up to the fraction, let's say, or up the fraction here? So of course we can say second equal to hertz negative 1 as well, or power negative 1 as well. So just be careful. If you see something like this, these are both correct. And by the way, if you're going to take a look, what happens if I cross multiply this? What will I get? I'll get, let's use red this time. So we can say period times frequency. What happens at the other side? Well, what will be remaining? Of course, is 1. That means that if you ever multiply the period by the frequency, you must always get 1. If you don't get 1, of course, you've done something wrong. Go recheck your work here. Okay, so now let's go back to this. So what is period? It is the time it takes to, or takes a complete cycle to occur, yeah? The time that it takes for one complete cycle to occur, to happen, that is basically called period. What about frequency? By the way, period is measured in second, or it can be measured in hertz negative 1. Don't forget that. What about frequency? Of course, we can say frequency, it is the number of cycles or vibrations per unit time, yes? And of course, it is measured in hertz or second negative 1. And these are the equations for both frequency and the period as well. Frequency equal to 1 over t, that is the period, and time or period equal to 1 over frequency. By the way, we can also use another equation as well. We can say frequency is the number of waves per unit time as well. Let me give you an example. Let's say you're sitting by the beach or on the beach, on the shore. You'll see that 10 waves make it to the shore, okay? Let's say you'll see that 10 waves, okay? These are not 10, but 10 waves make it to the shore in 10 waves, right? Make it to the shore in, let's say, 2 seconds, yeah? So what is the frequency of the ocean waves in this case? We can say frequency equal to number of waves, number of what? Number of waves, right? divided by the time, or period, yes, divided by the time. We said there are 10 waves making to the shore in 2 seconds. So 10 divided by 2, of course, that is 5 hertz, yeah? So we can say the frequency of the ocean waves, that is 5 hertz. What does 5 hertz means? That means there will be 5 waves coming to the shore every second. Don't forget that. What if I tell you how many or how much time will one wave take? That's a very good question, yeah? So remember this. If the frequency is 5 hertz, what would be the period, the time for one wave? In this case, we can say period equal to 1 over frequency, 1 over 5, and of course you can divide this one, that is 0. What? 0.2, I hope, yeah? So 0.2 what? That is going to be 0.2 second. That means it takes 0.2 seconds for each wave to get, or let's say to come to the shore. Okay. All right. You can double check with the number. I think it is correct though. Okay. Now, so frequency, we said if number of waves given and the time is given, you could just divide the two to get the number of frequency. By the way, when do we say one swing? Didn't we say that period is the time for one complete wave? So what is one complete wave? Take a look at this diagram here. Remember, in order for, let's say, if you're starting the time at this point here, then the time must be running all the way. Remember, this girl has to go to the middle and then all the way to the other end and then come back all the way to this point here. Then that is called one cycle, one swing, or the time for one period, you can say. Okay? That is going to be the time for one complete swing here. All right, now take a look at this one here. This question is also very interesting. What is the total distance traveled by an object moving back and forth in a simple harmonic motion in a time interval equal to the period, okay? Or equal to its period when it is amplitude equal to A, okay? Of course, we have this one here, but let me take you back to this, yeah? Remember, we said one period, that is basically the time for one complete swing, one back and forth, yeah? But look, if we started this here, this is basically what is called amplitude here, yeah? So we have one amplitude to this point, and then one amplitude to this point. So there are two amplitude for half a swing, okay? And then, of course, remember this, that is 2 for going, and of course, one amplitude to come back to this point, and then another amplitude to come back to this point. So how many amplitudes are there in one swing, let's say, one full cycle, one period? Of course, there are 4 amplitude, okay? Remember this. Because, let's clean this a little. Remember this. This person has to go all the way to this, that is 1 amplitude, yeah? And then go all the way to the other end, that is 2 amplitude. And now it has to go back, yeah? So this is 3 amplitude coming to this point, and then covering the last section here, that is another amplitude. So there are 4 amplitude in one complete swing or one period, okay? Remember, because we said period is the time for one complete swing. Okay. And then so now you can see here, if we start at this point here, from point A to point B, that is 1 amplitude, point B to point, let's say A again, that is 2, all the way to C, that is 3, C again to A, that is 4 amplitude. Remember, no matter where you start, you'll have to go back to the same point in order to cover one complete cycle, okay? So if you start at the center, at the equilibrium, you'll have to go all the way to B and then to C and then back to A, then you have continued or completed one cycle, let's say. But if you start from C, you have to go all the way to B and then back to C, then that is one complete cycle. So of course, we can say the total distance for one swing, it is 4 amplitude. What if they say half, like what is going to be the total distance for half a period, okay? For half a period, that means half a cycle, and for half a cycle, of course, it is just going to be what? Let's say if we start from C, it's going to be C to B, that is half, yeah? And of course, 1 amplitude, and that is 2 amplitude. What if they say, let's say, what is the distance traveled of a simple harmonic motion and time interval equal to 2/8 of its period when the amplitude equal to just A, yeah? Remember, it says the time interval equal to 2/8, yeah? So of course we can say 2/8, that means 2/8, yeah? in a time of 2/8 of this period, we know that in one period there are 4 amplitude, yeah? And of course now you could divide this two and simplify, of course, then of course is going to be 1 amplitude. So in a time interval that is equal to 2/8 if it is amplitude, of course, or if it is period, then of course is going to be 1 amplitude. Or another way you can say 2/8 is going to be 1/4 if you simplify, and 1/4 because we have 4 amplitudes here, so 1/4 that would equal to just multiply by 4, you will just get 1 amplitude. And of course we have one study tip, and that would we will be covering this one for next time. That is like what will happen, for example, if you have the number, let's say how many times does it pass through the equilibrium, how many times or how many amplitudes were given, then how do we use these information to find the frequency. So stay with us, keep practicing, and I'll see you next time, inshallah. Assalamu alaikum wa rahmatullah.